so let's start with Electricity and Magnetism Part 3. If you are following along on Twitch, you can write !Discord, hop in the Discord to grab the notes. If you are following along on YouTube, all of that stuff is down in the description below. And for some reason, my YouTube subscriber count, majority of people that actually watch my stuff are not subscribers. So if you'd like to support the channel, subscribe on the YouTubes, and that will definitely help support the channel. But yeah, so most of the watch time on my YouTube channel is watched by people who are not subscribed. So don't forget to do that. And yeah, can you throw up the YouTube as well, NC? That would be helpful as well. In case anybody in chat would like to follow along. Like I said, I put these all up on YouTube, so the parts 1 and 2 are up on YouTube, and you can. Nice, Tropical. Nice. So you can go to the YouTube to get caught up if you'd like to. So parts 1 and 2 are up. And then I have other discussion series as well, including path integration, Lagrange mechanics. You guys are all, you know the deal. So let's start with little E and M. Part 3. Today we're talking all about potentials. So last week, let's do a little last time. Last time we talked about the Gauss's law of prescription. And I won't go into detail. I will talk about it, but I won't write it out online. Or on the board, I thought that there might be some decent, that I should add one more thing to it that I normally add when I talk about it to my class, but I was trying to generalize it, and I think it's okay if I add this step, right? NC's in charge during the meeting, awesome. Okay, sounds good. I wanted to add another step, a first step, and that is, again, these are in my notes, so if you'd like to follow along. They're on Discord in the channel discussion series notes. So Gauss's law, prescription should really go like this. The first step should be recognize the symmetry of the charge distribution. So ultimately, Gauss's law is about finding the electric field away from some distance away from a charge distribution, right? And recognizing symmetry is all about what Gauss's law. 2, we solve Gauss's law equation. So I will write this down. This is the Gauss's law equation, and we do need to solve it. That's the biggest point of the Gauss's law prescription, is to solve this equation. And what we do is we want to solve it in terms of e as a function of r, right? So to some yada yada. And this is going to be with some q enclosed over here, and we'll have remember, this is always nope. Haha. That's the potential one. Yeah, so yes, we're going to solve the electric field in terms of R. We're going to want Q enclosed to be on the right-hand side, because step 3 is to find Q enclosed for each particular Gaussian surface. And I'm reading straight from the notes. And then 4 is profit, right? Finding Q enclosed for each particular Gaussian surface, depending on what the problem states, that is important for...
Please go over Helmholtz decomposition.
No. We'll see. I don't know. If Griffiths does it, we'll do it. If Griffiths does it, we'll do it. If not, I can do it on a separate time. And then we'll just slap it in the E and M stuff.
Darn. I never prepare for yada yada.
You can prepare. You don't have to prepare for this. Just follow along in the notes. It's all gravy. So then after we find Q enclosed for each particular Gaussian surface, then we're good. Then we've solved the electric field of some charge distribution. And then after that, we talked about the 3 different symmetries of the Gaussian surfaces and the charge distributions that we're interested in, right? Gauss's law works for 3 main symmetries: spherical, cylindrical, and planar, right? Those are the symmetries that we cared about. So we did a couple examples, right? We did the example of a sphere, of a uniformly charged sphere, and then we did the example of an infinite plane. After we did that, then we moved into finding the potentials, right? So we derived a second Maxwell's equation, which is the curl of the electric field is equal to 0. But that's only the second Maxwell's equations for electrostatics. Once the charges begin moving, then that will change, right? But we did do the second Maxwell's equations. Remember, this discussion series is all about the Maxwell's equations, trying to derive Maxwell's equations. And then once we got the second Maxwell's equations for an electrostatic, we were then able to realize that led to the electric field equation. Let me write that down. So, we should write them both down. So we had the curl of E is equal to 0, and the that led to the electric field is equal to the negative gradient of the potential. Okay, and we did all that last week. Hey, Koopa! I think Griffiths briefly goes over Helmholtz decomposition in the appendix, or the first few pages. Okay, so if you remind me, NC, we'll do that as like a special thing on like Friday or Sunday or next week sometime. And then we'll just slap it into the YouTube VOD collection of E and M. Now, let's talk about potential. Okay? So now we're on to part 3. So let's more on potential. Not more on potential. Not more on potential. More on potential. You get it? Okay. Let's see here. Name a potential. Okay, so the name. So let's talk about the name for a second. Legitimately, though, Helmholtz decomposition in the back of Griffiths is really nice to understand. Transition to electromagnetic gauges. Okay, then maybe we'll do it. Like for serious, just remind me, and I'll slap it into the agenda. If it's that helpful, I want to make sure we talk about it, because again, this is stuff that could be helpful to everybody. So, okay, so the more on potential. We have to talk about the name potential, which is a misnomer, right? Because everybody up until this point in their introductory physics class hears potential and immediately thinks potential energy, right? And they're not separate. They are actually really closely related, but they're not the same thing, right? They are a little different. So, we're going to get into a little bit of that later on in Griffiths, but for now, potential and potential energy are separate but closely related. And then if you take the intro physics class, you remember that the big difference between electric potential and potential energy is potential energy is going to be that energy from two charges. The potential energy associated with two charges, or I should say the electric potential associated with two charges. And then potential is, some potential away from a single charge. And then, like I said, we'll get into that in more detail later. But for now, let's move on to another thing, and that's the advantage. And these are all in Griffiths. As you know, I'm following along with Griffiths. So if you would like to follow along, that's how you do it. So what's another another point? So let's just say, I don't know if I want to write all these out, but we'll do it anyway. So the name potential is a misnomer. Misnomer. But it's not too bad. We can figure it out. And then the next thing is just going to be advantage. What's an advantage? Well, with the advantage of the electric field is equal to the minus gradient of the potential. Well, there's two things, really. And that is that we can, there's one thing, but there's two variants of that thing. And that is that we can get either V or E from one of them, So like if we have E, we can get V. If we have V, we can get E. So that's really helpful, right? That's a very, very good thing to have. And a big advantage is to know have this relationship right here because, excuse me, then we can get one or the other. And what we'll do is we'll find, how to get E or how to get V if we know E because we learned Gauss's law and we have the prescription. So if you're good with the prescription, then you can just get Gauss's law and then figure out the V from that. Or if we're learn a second way to learn how to do V today. And then once you solve that, if you need E from there, you can get E that way as well. So the third thing to say is about a reference point, right? So the third point to make about potentials is reference point matters, right? And we can figure that out relatively simply. Suppose we want to change the reference point of potential. So we're going to call this potential V. Now remember last time when we did the potential, we have V of R. Now we're going to say, okay, we're just going to move to a different origin. So if this is our point charge, and we didn't really do this yet, but we're just going to sort of say, this is our point of interest, and, we have some origin here. So we have like this, and this, with our different vectors. I don't want to get into it yet because we're going to go over this in kind of a detail. But what if we just take this and slide it over to a different spot with with a different arrangement of vectors? Well, that's not a square, that's a prime. It matters in the sense that it doesn't matter at all. Well, don't spoil it for everybody. It matters in some sense, but really what we want to say is that the goal is to always talk about the potential difference. And in that sense, it doesn't matter, like NC was saying. Minus the integral from... So what we're going to do is we're going to take this integral, the same one we had last time, except this time instead of starting from, this origin, we're just going to shift the origin. So now we have a different origin, and we're just going to evaluate the potential, right? And what we'll get is, the potential from the new origin. We're going to split that integral up into two integrals. So we'll go from the new origin to the old origin of E dot dl. And basically just extend the line now. Because remember, the whole point of this was to talk about how as long as this is true, then we can get this. So this is the curl, so it's how does it change along some line integral. And finding out that it doesn't change along the line integral was very important. So that means we can split this up into the two integrals. So now we have a new integral from our old origin back to our point of interest. And what we found here is that this just turns out to be our old potential, right? The potential from one origin, or from one point in respect to one origin versus the potential from the other. So this just became some constant because it's just a line integral from one origin to another origin. It doesn't really matter too much, but it's just some constant plus the old potential. Okay? Oops, no prime, right? The old potential. So now we have some constant times, or plus our old potential. So where does that lead? Okay, let's make sure we finish this and show that really the derivative, or not the derivative, the difference is what we're interested in at. Because if we think about it, then we'll just have, some VB minus V prime A is equal to some VB minus VA. And since origin is just, origin is not, changing the origin is just a factor of a constant. It's going to be a constant on both sides of this equation, right? Because the r is what we really care about. So we'll just end up canceling it away. So it'd be really like if we were to have k plus this, plus k, and then those are going to cancel away. Okay. So that's another nice point to note, is that it doesn't really matter if we have the potential, or if we move the potential to a different thing, as long as we're talking about the potential difference. So for that reason, it is a good convention, right, to take the potential at the origin, to take it to infinity. Because then, remember, the potential is an inverse function, right? It's inversely proportional to the radius, I should say. So that means if the radius is infinity, then this is going to be 0, okay? So that's just by convention we say that this is what we want, right? Is the potential of some of our origin to be at 0, or at infinity, excuse me. So the potential is 0. Another point of interest we should say, number 4, is that potential follows superposition. Everything else did, right? The electric field and the force. So as it's just convenient and relative to the next few statements. And we have a basic example of a gauge, exactly. Definitely. So the potential is a superposition. So we can write the potential as a superposition. And then lastly, we should just mention units just for everybody's safety. Units are, best if set to 1. But if you want to be useful, then we consider the two unit conventions, either Newton meters over coulombs or joules per coulomb. Okay. So those are just some interesting things to talk about potential. So now let's get down to some examples. Let's do some nitty gritty. I told you that we would use this, so let's do that. And that is the idea that if we have the electric field, we can find the potential. So let's do that. Having the electric field, finding the potential, very, very useful. So let's have a sphere, a spherical shell. So here's a spherical shell with some radius r, okay, and some point of interest. Actually, let's put the point of interest here, P, and our origin is at infinity, so we're going to do, coming in from infinity out to that point. Okay? I know, right? I tried to set them equal to 1. But this is... Griffiths wants us to be more careful, I guess. I don't know. He doesn't get it yet. You know, he hasn't watched my stream, I guess. So the goal is to find the potential inside and outside of a spherical shell of radius r that carries a uniform surface charge. All right. Now this one, spherical cow needs a tail. Yes. Now this one is, we can start with Gauss's law, electric field. We can figure it out. I'm just going to write the answer down, but you can figure this out with Gauss's law pretty easily. But if you remember that certain outside of a shape, a spherical shape, and we did this with a spherical density, or I'm sorry, excuse me, a uniform volume density. But this is always going to be, you know, it's going to be treated like a point charge when it's outside, and we can talk about the total charge. If you know the total charge, you can treat it like a point charge, right? Hey, Ash! No, don't panic, don't panic. It's treated like a point charge, okay? Hey, Jax! Good to see you, good to see you. And also Ash, good to see you as well. Now, like I said, so we have a spherical shell of uniform charge. So we're going to treat it like a point charge on the outside. And that means we can just sort of take the potential of the negative integral from some origin that we defined kind of, you know, purposefully at infinity. And we're going to take it all the way to R, which is where we want to consider the point of interest. So right now it's outside, but then the next one we'll have to do is move the point of interest on the inside, and then we'll have to extend it a little bit farther inside. Okay? Oh, what does that mean? So that means we have negative 1 over 4 pi epsilon naught times the integral from infinity to R. Right now I'm just plugging in this E stuff and this infinity from the origin. And we'll get this factor will come out front. Here's the minus sign right there. And last thing we have is q over r squared. Q over r prime squared, excuse me, dr prime. Now, because I know what EDL is, we'll actually do this dot product out a little bit later, but I should just remind you, we did it last time as well. So I'm not going to show it this time, but we'll show it later today. But this E.dl is going to get rid of all of the other terms except the radius, right? This is perpendicular, parallel, excuse me, with the radius, and that's the only thing that will survive, okay? And, let's see here. So then we can do this, is that it? Oh, no, I should simplify it. I should do the integral, that's important too. Oof. Okay, so we're doing this integral, we get 1 over 4 pi epsilon naught. And we get q over r prime. And then, so the minus from here, and this is r squared, so taking the integral of that, we get a minus out front, and we raise this to the power of negative 1. And that means the integral is going to be over from, the evaluated at infinity in r. Now, like I said, this is by convention on purpose, right? So that way, if we take it to be infinity, then we know that that's 0, so the second part of this is going to go away. If you'd like to see it, I'll write it out anyways. Oh, like that, I guess I don't have to. It's relatively straightforward. It's just q over infinity, which is 0. And then this is just going to be 1 over 4 pi epsilon naught times q over r. Okay? Now, to find the potential inside, we'll break the integral up into 2 separate integrals, right? So right here we have this, and that was good. That's all we needed. But now if we have something different happening on the outside and inside, we're going to have to split it up so that it stops at the surface and restarts at the surface. So this is for, for outside, or r greater than r. And now we want to do for inside, or r less than r. Okay? So we'll do that again, and it's relatively the same prescription. V, a function of r, is going to equal the negative integral from...
I forgot how much I hate doing integrals.
from the origin to r. Actually, we can skip the first step because we know we have to split it up. So let's just skip the first step of writing out that same integral again, and let's just write the split integral. Okay? Like I have in my notes. And it's negative 1 over 4 pi epsilon naught. The integral of infinity to r of q over r prime squared dr prime. And now notice how I'm stopping at the inside as the inside radius, right? That's when I hit the outside. So that's coming in from infinity and stopping at the surface. Okay, but there's still more to it because now we're at some point of interest inside, right? So we'll have to come all the way down into there as well. Just imagine that's an accurate picture. And we get what? So now we're going from some r radius, from the big R to some r radius on the inside. And the nice thing about this is, what's the charge enclosed? Or what's the charge of the inside? Remember, this was Q enclosed, and that's going to be 0. So this whole thing is going to be 0. dr prime.
Welcome to the channel. Things get a little bit weird.
Fire Bear, welcome to the channel. Fire Bears, there's plural. Welcome to the channel. Thank you for the follow. Okay, so now we can do these two integrals. This is this one's just going to be 0, but this one's not, so we should write that one down. And what do we get? We get 1 over 4 pi epsilon naught q over r prime evaluated at r and infinity, and then plus 0. What? Excuse me. Okay. Oops. Cord caught. Now, then we can just evaluate this. And what do we get? We get 1 over 4 pi epsilon naught q over r. Now, this is an interesting result, right? Because this is constant. I'm assuming you can see, even though you can't see me. Hello. But this is constant, right? This r is just the radius of the sphere. Yeah, so this is constant, which means that the potential is non-zero. It's not 0. Even though there's no charges enclosed by some like object in here, it's not a 0 density. Or it's not a 0 potential, excuse me. It is a 0 charge density, but it's not a 0 potential. There is potential there, but it's constant. It's not changing, so I think that's interesting. So here we have our two potentials. We have one that depends on r and one that does not, that it's constant. So we did that. Next up, we have... I think we're going to start talking about... Okay, so we have Poisson's equations and Laplace's equation. Now, every time I pronounce the word Poisson, everybody takes to the keyboard and wants to sit there and speak it out, and everyone's got to try to sound it out phonetically. Okay, we get it. I'm going to say Poisson, okay?
Poisson.
Yeah, here we go. As soon as I said Poisson, I guarantee you... Okay, let's do it. Poisson's equation and Laplace's equation. I don't know where I would be without you guys, but I'm happy we're here. That's for sure. And Laplace's equation. Poissonwish. What does that mean for the first of Maxwell's laws? Oh, Gauss's law? The first of Maxwell's equation is usually derived from Gauss's law, which means that there is no electric field. Okay. Poisson's equation and Laplace's equation. Let's say, so can we consider the divergence and the curl of the potential? We know the divergence and the curl of the electric field, right? We did that, and this is, Gauss's or Maxwell's equation, the first one. And this is what Castellano was talking about. And we have the, density, the volume density divided by the epsilon naught. And then we also have the curl of the electric field, which is Maxwell's second law for electrostatics, where it was equal to 0. And what does this mean for potential? Can we figure something out using our E equals negative? I forgot the negative in the notes. So slap a negative on that gradient of potential there at the bottom of page 2. So, okay, so let's start with this one, right? And can we derive it? Sure. Well, let's say we want to do, the divergence of, the negative divergence of V. And that's going to equal negative, surprise, it's a Laplacian, right? we have the dot product of the divergence or of the gradients times the v, and that's a Laplacian. But moreover, this Laplacian, I don't even need this implies. I can just straight up write equals, right? So moreover, we have a Laplace or a Poisson's equation where we have the second order divergence of the potential is equal to, I don't know if you call it second order divergence. That's what I just always refer to it as. Is equal to, I should say the positive second order divergence is equal to the negative volume density over epsilon naught. Okay? Wait, but Eric, is that thing on the right you were saying no charge enclosed? Yes, this is just a spherical shell. Yep, that's why the potential inside, or the potential outside is treated like a point charge and the potential inside is constant. Yep. Whereas the electric field on the outside is still treated like a potential. It's still treated like this, but the electric field on the inside is actually 0. Arcus89, welcome to the channel. Thank you for the follow. Okay, so what happens if we have no charge enclosed, right? So for this one specifically, right, what happens if we're considering where the charge density, the volume charge density is 0? Then we can talk about the Laplace equation, or yeah, then we can talk about this setting. This is actually equal to 0. Let's rewrite it though. I don't want to. Let's keep these names correctly. This is Poisson, and this is, and if the volume density is equal to 0, then this is going to be 0, and this is Laplace's equation. Laplace's equation. Okay? And those are going to be much more relevant in Chapter 3 when we get there. It's good to have you, Arcus. If you do have any questions, you can write exclamation mark space in the question, and we'll go into a separate thing that I can take a look at when I'm done with our discussion series lesson. Now, so now we learned about Laplace's and oh no, we didn't do the curl yet, so let's do the curl too. That's important. So we have this one too, so let's see what happens when we do that. We'll have you know, the curl of the divergence. And what does this mean? Well, these are going to be the same vectors, so this is going to be equal to 0 as well. But that's kind of to be expected, right? Because we kind of set this way up in a way where, like, remember, this is now it's a little bit of circular reasoning because we actually defined our E is equal to the negative divergence of V, specifically using this as the basis for finding out that the integral, the line integral, does not change. Okay. Yes, exactly. Oh, yes, exactly. Very good, very good, Jack. Thank you for the clarification. I don't often know what I say. Very, very good. Thank you so much. Okay, so let's do... Okay, so that's that. And then, like I said, this is to be expected. So no big deal with the curl. It's equal to 0. But this one will be relevant a little bit later, the Poisson's equation versus Laplace equations, once we start dealing with
Dear Anubis, that was painful.
Potential.
Okay. Now physics.
It's good to have you. Welcome back to the real world where we're all excited. I'm going to erase this equation, this side. So yeah, so this is going to be a VOD. So if you do want to come back and take a look at this, you can follow me on YouTube, and I'll have the VOD up in the next couple days, where it's just kind of trimmed down. You don't have to watch an entire stream to get to this. It's just going to be the lesson with less of my own nonsense involved. Let's see here. Potential of a charge distribution. So let's see here. Potential of a charge distribution. Now,
I was considering sticking a knife in my ears, but it ended. So where are we?
Sparkman321, thank you for the follow. Welcome to the channel. So we are on potential of a charge distribution. So far today, we had a little bit of a recap with Gauss's law, since that was last week, and then again the intro to the potential last week. And this week is all about potential. So we kind of talked about 5 of the key notes. Griffiths calls them remarks on potential. And and then we talked about how you can, use that equation, the electric field is equal to the gradient of the potential, to get a lot of stuff. But now we want to do something different. We want to talk about the potential of a charge distribution. And do you guys remember what I specifically said? And this is always the way I teach my intro physics class. So Bachman, if you're here, this is you. The what was the specific thing I said about finding a potential?
Nothing. good day, sir.
That is
That's
the
Tyrion.
You want to find, if you can't find a potential from a certain shape, you should start with what you know, which is to find a potential of a point. A point occupies 0 dimensions in space. So if you are clever with your integration, you can figure out how things work by occupying 0 dimensions, like a point, and then you can integrate that into some shape. Okay, that's how we did. We can do that with electric fields.
Really?
Just Q, Cosmolano. It's just Q. That's it. That was just the potential on the shell. Total potential, or total charge. Excuse me. Total charge on the shell was Q. So that's how we start with the electric field, and then we moved into the potential. So let's consider again the electric field of a point particle. Okay.
NC is such a tattletale.
Would you two behave? Q to R squared times dr. Now, let's also think about what this dl means, okay? Because dl has a certain role to play in this as well. And I told you would see this again, but I want to write out the whole thing. So this is how you go from cylindrical, or not cylindrical, Cartesian coordinates, or rectangular, to spherical, which, you have to pick the appropriate coordinates to solve the appropriate problem. And this one is spherical. Because... did I skip something? Oh, no. Well, we'll just do this one for now so I can show you guys. So now, because it's a point charge. So a point charge is going to have a spherical symmetry. That's why. Okay. I thought we were already to the next example, which we're not. Then if we have v to the r, or v as a function of r, is going to equal, so for a point charge, let's think about the electric field. So we have minus using the same trick we used over there, from some origin to some r, E dot dl. Now we can actually write out what E dot dl is, just like we had before with the dl. Ooh. Why is there a d there? This is just supposed to be r hat. It's a point charge. Oops. Let's erase that from the notes. Am I missing something with his notes? He didn't write that, did he? That's probably just me. Yeah, it's just me. He didn't write that. So in the notes, I have an extra d in that equation. The first e. It's not supposed to show up as dr until that line below it. I meant, was it just on the shell? Yep. It's just a charge distribution on the shell. Okay. R hat. There we go. Okay. So that's fixed in my notes. Hopefully you fixed it in yours. And now we can write E dot dl. I kind of skipped it. I think I was moving a little too quickly. But let's just write E dot dl down here, and then we can just plug it in right there. E dot dl is going to minimize all this by just letting this r hat and this r hat be dotted together, which we know is 1. And since r hat, theta hat, and phi hat are all perpendicular to each other, then these two contributions are both 0. And we'll get E dot dl is equal to... Yo, hey Roma, what are you doing? Okay. Come on, where's that buttery complexion that we know and love? 1 over 4 pi epsilon naught times q over r dr. So there we go. Now it's you'll see Cosmolano. I haven't got there yet, quite yet. So what we have here is E dot dl is equal to this. So then we can plug this up here. And what do we get for the potential? We'll end up getting... You're trying to butter me up, aren't you? Infinity to r of q over r squared dr prime. These are r primes because, again, we have r prime as the dummy variable for r. And then this is just going to boil down to what you would expect it to be for the point charge, 1 over 4 pi epsilon naught q over r. And it's a scalar, right? Which is good because it's potential. So we want v to be a scalar. So, all well and good. Now we have the potential due to a point. Okay, but that's not quite good enough, right? I told you we want to find the potential due to a point, and then we can extrapolate it into some surface charge density using integration. So let's think about that for a second. Let's do. I still didn't want to erase that, but I guess we're gonna erase it. That's okay. I think it's okay. We'll just leave this the object. And I wanted to get those electric fields, but you'll just have to remember what they were. Hasn't been that long, has it? No, not at all. Now, if we just have a point charge, right? P and the charge Q, then we'll just have some line between the two, and we'll just call that crazy R as the radius between the charge and the point of interest. And like I said, we have that law of superposition, so we could consider a bunch of point charges, Q1, Q2, and then just have the Qi, and then we'll just have each of them will have some crazy R associated with the charge away from the particle, and then we can just add up all of the potentials, or the point of interest, and then add up all the potentials. But now what if we have some weird shape? And this is, I think, getting to the root of what Caswellano was asking, right? How do we do this with a shape? Well, what if we have an infinitesimal small chunk of that? So imagine that square is infinitesimally small. It has 0 dimensions. So this infinitesimal small piece of this, we're going to give it a label d tau, okay? That means it's going to be infinitesimally small volume piece of that object, okay? Remember, Griffiths uses tau as a volume variable. Now what we can do is we can define some point P and figure out that there's some crazy R distance away from it, and we can find the potential at that point P, right? It's very important that we have that. And if we do have an infinitesimally small spot that occupies 0 dimensions, then it is, in fact, a point-like object, and we can treat it like a particle, a point-like particle. Now, the goal is then to take this d tau and be able to integrate it into a shape. And like we've seen in the past, that's how we're able to extrapolate these different Jashuk. I hope I said your name okay. Welcome to the channel. Thank you for the follow. If we extrapolate this small dt into this shape, then we can find the potential of this whole shape. Just like summing up all the individual points does, now imagine there's an infinitesimally small amount of points on this, and we're going to integrate all of those points just like you would add up in a similar fashion to adding up via summation. Okay?
Things get a little bit weird.
More friends. Lady Coco, thank you for the follow. Welcome to the channel. Okay, so after we integrate up into, the shape, and I have in the notes, again, if you are just getting here or new to the stream, we do the discussion series. Right now we're doing it twice a week until I start school again, and then we'll see what we got. You can press !Discord to hop in the Discord, and I have a channel called Discussion Series Notes, and all of my notes are there, so you can just follow along. Reboot to you. Thank you for the follow. Welcome to the channel. You recognize the symbol. No, it's not at all. So integration, it's an antiderivative. So if you're good with the derivatives, then you can, extrapolate backwards to do the integral. But it would probably be good to practice some of this. So if you have any questions, then we can talk about it afterwards for sure. Because we're going to stick around and talk for a while after this. I got a couple other things planned for stream today. So if you are new here, is this Stokes' theorem? Stokes' theorem is used in a way to get... It's similar to Stokes' theorem, but Stokes' theorem doesn't really say anything about this method.
Discuss.
I don't think.
Because.
Thank you, Craig. Stokes' theorem is similar to this, but I think you use it for a different purpose. Like that's how we used to find out, the derivative form of Gauss's law as opposed to the integral form. Heisen, thank you for the follow. Welcome to the channel. Okay, so now we have this shape here. We can integrate it up. I have in the notes all of the different potentials, the point versus the points versus the surface. But I'm going to write the surface one down because that's going to be relevant to solving our example here. 1 over 4 pi epsilon naught times the integral of 1 over crazy R dq. Now that dq is the same thing as we discussed integral form. Good to see you, Eisen. If you have any question, Heisen, just ask, and then your question, and then we'll go to a separate queue, or you can just stick around and learn some E&M with us. This is all very casual. It's not associated with the university. It's just what I do in my free time. So, Feel free to ask questions, because this is for you people, my friends on Twitch. So this is the infinitesimal small charge that we're treating like a point. So that's the thing. It's like this is an infinitesimal small volume, and associated with this infinitesimal small point. This is very specific to say that this has to be an evenly dispersed charge distribution, right? Why? Because we need these different things. Like we need our rho, which is going to be total charge over total volume. But it's also going to be this infinitesimal small charge over this infinitesimal small volume. Like, that's very important. And then we have, so that's for the volume. We could do the line, which is going to be the infinitesimally small charge over the infinitesimally small line. Same thing, except instead of a three-dimensional volume here, we'll have a two-dimensional volume. And lastly, we can talk about sigma. I'll just write it over here, which is just the infinitesimally small charge over an infinitesimally small area. Okay? This is an A, not a Q, even though it looks exactly identical. But with this one is specifically, we can then extrapolate this one into a new version of this, which is going to be VR is equal to 1 over 4 pi epsilon naught integral of rho r prime over crazy r d tau prime. Okay? Though this is at a university, it's true. Well, I can't wait to get back to my garage. I usually, during the spring, summer, and fall, I'm in the garage. And then during the winter time, I have to come here because it's too cold in my garage. But yes, that is the potential, the integral form of the potential due to some volume charge. Now, let's go back to this example, which is why I wanted everything to stay up there. I want to talk about that example specifically. But I guess I'm going to have to draw over top of it anyways. Let's get rid of this. And the idea is going to be, so we have a shell, a spherical shell. And this time we're going to put it on a plane. So let's get rid of this. And instead, we're going to have some point on the z-axis. So this is going to be the z-axis. And then we'll have an x-axis, or I'm sorry, a y-axis and an x-axis. And get rid of this point from the inside. And now we'll have the point on the z-axis. Okay. So now what's going to happen is if we were to pick some spot on the surface, say like right here, okay, this is going to have a dA, you know, a dA. You can vector it. It's just normal to the surface because we're having a surface charge distribution. Okay, surface charge distribution. So that means the spherical shell. You can imagine the shell is infinitely thin in width. So the point on the surface. Oh, jeez. I can't believe I just read that. Anyways. Got me good. So now, if you go from the origin out to here, let's get rid of this because that's our real radius right here. If you go from the origin out to the surface, that's obviously r. Right? So the distance from the origin to our infinitesimally small piece is just going to be r. And then the difference from, or the distance from our infinitesimally small piece to our point of interest is going to be crazy r, right? That's always been that variable. And then up to here is just going to be, what do I have that as? I think it's ill-defined. It is ill-defined. We don't really need it. I think we called it z. So from here up to this point, we called it z. Okay? And that tells us we can use the law of, so we're going to redefine our v, but this time in terms of 2 dimensions. So our potential is going to be 1 over 4 pi epsilon naught times the integral of our surface charge density over crazy r times r.
I can't find the reference in Griffiths to anything called crazy r.
You see it. It's this cursive r or whatever. Man, you're gonna. What do you do? Okay. We're almost done. We have this example is it, and then we're done for today. So we have the potential is equal to this thing now for 2 dimensions. We also need the law of cosines. Welcome to the channel, Kostolf. Good to have you. Thank you for the follow. Let's do crazy r squared is equal to capital R squared plus z squared minus 2rz cosine theta. That's just the law of cosines established with this triangle that we made right here. Good? Excellent. Law of cosines you can just look up in some table if you're interested. Fun fact, Griffiths made available his crazy R in LaTeX. I don't know. We can talk about the infinitesimally small, piece on the surface, the area, the infinitesimally small area, and that's going to be r squared sine theta prime d theta prime d phi prime. I know that looks like a squared, but it's not. It's just d phi prime. Now, how do we get that? Again, this is best done with the table. If you'd like to extrapolate how to do the area of a spherical from rectangular to spherical, you can do that, but that's a bit of a bit of hoops to jump through. I really dislike the use of separation vector. I feel like it hides what's happening in the integration. Physics, your favorite subject. Awesome, Kostov. Welcome, welcome, welcome. I don't know. Maybe it is happening with what's inside the integration. I think that, like, you should be comfortable enough where at some point you should be able to skip it. But I definitely understand what you're saying. Ludes2000, welcome to the channel. Thank you for the follow. I definitely understand what you're saying. It does definitely hide some of the stuff inside with what's going on with the densities, right? Like the densities, you're really taking. I mean, this is a bit of a cop off for the densities, but after you do it enough times, you should be pretty comfortable with it. Now, the cool thing about this is let's talk about that. Actually, I have it in my notes. What's the surface area? Well, we can take the integral of dA, right? That's kind of a relevant thing. And it's good to see. So let's just take the integral of it and see what happens. This is actually a double integral with one going from 0 to pi. And so theta goes from 0 to pi and phi goes from 0 to 2 pi. That's basically how you make a two-dimensional sphere. You take one thing, right, and you rotate at pi. So if you take a line, a radius, and you rotate at pi, you're going to get a two-dimensional semicircle, right? Half a circle. Two-dimensional half a circle. So you start with a radius, you integrate it to from 0 to pi, you get a half a circle. Then you take that semicircle and you rotate that to pi. What do you get when you do that? Well, you take that semicircle, that half a circle, and you're integrating it, you're rotating it around to 2 pi, and then you get a full sphere. So that's the idea. And for this one specifically, there is no r factor. We're not making a solid line, so it's just going to be the area, so it's really just a point. So you make like that, and then it kind of looks like an arc, and then you take that arc and then you wrap it around. That's what the point of the area is, and that's how you get to the surface area. So when we evaluate this, we get r squared sine theta d theta d phi. Remember, primes are for dummy variables inside. And then when we evaluate this, we get exactly what you would expect.
The heavy water curve to show the sphere.
4 pi r squared. Apoplectic. I really need to know this 4 years ago, but it will probably take me another 2 years to understand. Yes. It's been a long time since I've taken this class too, so it's definitely a good refresher for me as well. But that's how we go from, that's what this really means, okay? So this process. And this is, without the r, this is known as the solid angle. Okay, which is the 4 pi, which is, yeah, okay. Anyways, and then if you wanted to make it three-dimensional, then this r, you have to include a volume, which has a dr term in here as well. Let's get rid of everything but the shape, and then we'll finish up here on this side. So now we have everything kind of set up for our last few calculations to get to the bottom of this. And, so let's just do it.
Welcome to the channel.
So if we start here,
Weird.
welcome, welcome, welcome. So if we start here, we're going to multiply this 4 pi epsilon naught over to the other side, and we'll get 4 pi epsilon naught times the potential, V, Z, is equal to sigma integral r squared sine theta prime d theta prime. Now, I know I did this, but I'm actually putting this integral back in here. So right now we have this dA going here, and sigma is going to be, oh, sigma's right there. I haven't gotten rid of it yet. Not yet. Soon, though. And then the idea is what's crazy r prime? Well, we have, or what's crazy r? Well, we have this right here, which we got from the law of sines. So, or law of cosines, excuse me. So we're going to put that back in. And what do we get? We get the derivative, the square root of that whole thing, which is r squared plus z squared minus 2rz cosine theta prime. Okay. Now I'm going to stretch it out much more because we've written it once and I want you guys to be able to see it. So I'm going to stretch this out quite a bit farther. So now we have 4 pi. Let's make this. We have 4 pi epsilon naught Vz is equal to. So we can start evaluating this a little bit. Right, so let's make this, we'll do the integral over phi, which is 0 to 2 pi, and there's only a d phi in here, so that's easy. That just means we get to pull a factor of 2 pi out of the integral, because remember this has 2 integrals, one for d theta, one for d phi, but this has a theta in it, and this has no phi in it. This has a theta down here too, so we have to be a little careful about that. But it has no phi in it, so it's just going to be a 2 pi. So let's pull that out, and we'll get 2 pi, and we also have an r squared in there we can pull out. And then we'll have the, and sigma. Don't forget sigma. And then 0 to pi now of our sine theta prime d theta prime divided by the denominator, which is r squared plus z squared minus 2rz cosine theta prime. Okay, now, next up we're going to do this integral. And this integral is not too bad. It really, I think, is a u substitution, if I remember correctly. I don't think it's a trig substitution. Maybe someone who's better at integration can remind me if this is a u substitution or a trig substitution, but I'm pretty sure it's a u sub. So what does that equal? It equals 2 pi r squared sigma 1 over rz, so this is going to be the result of the integral, times the square root basically what was in the denominator, r squared plus z squared minus 2rz cosine theta prime. Oh, and this is going to be evaluated at 0 and pi. So evaluated at 0 pi is going to be nice because then we only have the 1 theta in here. So evaluated at 0 and pi is good. There's both going to be 1s. And we're going to end up with this nice arrangement. So we evaluate them and they're both 1s. We're just going to get 2rz and... oh, I'm sorry. The 0 is going to be 1, but the pi is going to be minus 1. Okay, that's different. That means we're going to have extra minus signs to pay close attention to. But what it's going to boil down to, and again, I have this in my notes so you can just follow or take a look. But what this is going to boil down to is 2 terms. 2 pi r squared sigma times the square root. Oh, wait, this is all over. I'm sorry, this is not r squared. It's just r now over z because I pulled this factor out. So we get rid of one of the r's and then the z's in the denominator. And we have the square root of r plus z squared minus the square root of r minus z quantity squared. Now, this is nice. This is pretty nice because we have some square roots of some terms that are squared, so it's going to boil down to something really nice. But the thing is we have to be a little careful about this, right? It's a square root. So that means there's going to be plus and minus of each of these. So we have to think about it logically because we can't have negative radii, right? Like we need to make sure that everything remains positive. Remain positive, Tyrion. Remain positive. Don't have negatives in your square roots. So what's going to happen? Well, for the outside, we'll need to stick...
I hate you.
For outside the sphere, we'll need z minus r. And then for this term, this one doesn't matter because, I mean, well, we're going to just keep it positive for the whole thing. But this one, we'll need z minus r for the outside and r minus z on the inside. Okay? So let's write those out. And then we're going to move this stuff back over here, too. So you're going to see some weird stuff happen in this term. But it's just the 4 pi epsilon not getting back to where it's supposed to be. And that's going to be important because we're going to need to bring back in this sigma, too, at some point. We're going to need to evaluate that. So let's just see what we get. So for outside the sphere, we get r sigma divided by 2 epsilon naught z times r plus z for this one, and for this one it's z minus r, so it's minus z plus r, because we got to distribute that minus sign through, and this answer becomes r squared sigma divided by epsilon naught z, and again this is for out. Okay, now we're going to get one for in too. Let's just move along here. Z is equal to r sigma 2 epsilon naught times z. and then R plus Z minus R plus Z. And what do we get? We just get the other version of this, which is R sigma divided by epsilon naught. And this is for inside. Notice right now that sigma, remember I said sigma, hello? Remember I said sigma can't change, right? Sigma is a constant. It's a charge distribution. And then R is a constant, so this is just a constant. That's a good thing, because remember the potential is supposed to be a constant on the inside. That was one of the key things of what we found when we took the potential by finding the electric field. So, what else is next? Oh, let's plug in sigma, and we get the following. And this is where we stop. Woo! 1 over 4 pi epsilon naught.
Right outside the frame.
Is it really? Is just the N? It just says in. Yeah, it just says in. Good catch, though. I don't know if it's a Riemann positive. Is that what that means? I'm not 100% sure. Yeah, it just says in. That's all. So here we just have the last step, which is 1 over 4 pi epsilon naught q over r. This is for r greater than the radii. Now that's good, right? And I replaced z for r here because z is r in this one when it's on the outside. And then on the inside, it's just going to be epsilon naught q over r, right? Hold on. Let me double check. Yeah, for r less than or equal to r. Now this is really important because again, these are the exact same two answers we got before when we solved this problem using the electric field. Yes, this is more cumbersome. This is more challenging. You have this weird integral here. Blah, 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 blah. That's not nice. Nobody wants to do those integrals. So we have tables and stuff to handle that. But this is Griffiths makes this emphasis point. He says this is to emphasize the strength of this situation here. Right? Like we did the electric field, we did the opposite way first, right? We started with the point charge, and then we integrate, we extrapolate into the shape. And then we have the charge distribution into some shape, and we can find the electric field some distance away from that charge distribution. This we did it the other way around. We took the easier way, we did it first, but the problem is that's an easier way because we have to have Gauss's law to find the electric field. What if you don't have Gauss's law? What if you don't have the electric field? Right? Then you need this way in order to evaluate it. And then you can extrapolate the electric field out of the potential in the same way, right? E is equal to the negative divergence of E. Same difference. And that's it for today. That's it for potentials. Part 3 in the books. If you would like to get caught up, I know we had several people join in. This is part 3. Parts 1 and 2 are on my YouTube, !YT, if you'd like to get caught up with those. We are using Griffiths. We are, learning as we go.